So in this problem we're given a conic. This is a problem in 2 dimensions, and we're going to try and work out how to classify this one. This one's slightly different to the ones you've been doing, as you'll see, but the techniques are exactly the same, except this one is what we sometimes refer to as a degenerate case. It's going to turn out to be not one of the standard conics that you think of when we've looked at similar problems to this. And you might be able to see that immediately because you may recognise that this actually factorises as a perfect square. And so in that case you can see that this is just x plus 2y all squared is 5, and so you can out of that you're going to get 2 straight lines. Well, suppose you didn't see that, then we attack it in the usual way, which is we turn this firstly into a matrix problem, and we do that by writing this as xy times a matrix times little xy equals 5. And so as usual, we want that entry multiplies that entry multiplies that entry, so we get a 1. That entry multiplies that entry and that entry, so that's going to be a 4. And then we could put a 4 and a 1 there for that term, but that would be greedy. Instead we share the 4 equally amongst the 2 bits, and of course the advantage of that is it gives me a nice symmetric matrix, and so I have all the theory of symmetric matrices. So I'll call that matrix there A. And we need, of course, to work out the eigenvalues and eigenvectors for this matrix A. Well, we could go through and work out determinants again, but have a look here. If you just double that, you get that. So this matrix has determinant 0. And remember, the product of the eigenvalues is the determinant. So if one of them's 0, if the determinant's 0, one of the eigenvalues must be 0. And then from the trace, we get the other one. So you can do it by expanding out a determinant if you like, or you can just use your common sense and write down the 2 eigenvalues. Now the eigenspace for 0 then is going to be the kernel of, well, it's just the kernel of this matrix, and you've had plenty of practice at doing these now, so I'll take 2 of those and minus 1 of those, and that should work. And the eigenspace for 5 will be the kernel, I subtract 5 off the main diagonal. Always checking that the columns and rows of this matrix here must be linearly dependent. The determinant must be 0 because that's what we mean by the eigenvalue. And again, I look at this and say, look, I'll have 1 of those and 2 of those will do the trick. And you also double check it works on the second one. And notice also, again, this is where the theory is very lovely, because these are distinct eigenvalues, the eigenvectors are guaranteed orthogonal, and they are. So we can put, our P matrix then is the orthogonal matrix. I've got to normalise, so I'll have to divide by root 5. So there's the normalised matrix. And we make a change of variable. So we're going to put little xy is equal to p times capital Xy, where this new system are the principal axes. And so when we do that, when you plug it in, you get the usual thing. We end up with P transpose times this times P, and that will diagonalise it. And so that's going to give me capital Xy times the diagonal matrix, 0, 5, 0, 0, and then times capital Xy equals to 5. And when you multiply that out, you simply end up with y squared equals 1, or 5y squared is 5, so you get y squared is 1, and that gives you y is equal to plus or minus 1. Now, think about that. That means that y equals 1 is going to be a straight line parallel to the capital x-axis, and y equals minus 1 will be a parallel line. So in fact, as we mentioned before, this conic turns out to be 2 straight lines in the xy plane. And we're often asked to draw a picture of what this looks like graphically. So we draw a picture. We normally give the picture in 2 dimensions. We can show the little x and the little y plane. And the principal axes are going to come from the eigenvectors. So 2 minus 1 will be a vector down here. And that's going to be the new capital X axis. And the principal axis for the Y, because we put it in that order, if I'd done the other way around, then of course I would have got X here and then the picture would be a bit different. So, but the maths takes care of itself. You don't need to worry which way around, it's just the picture will look a bit different. So the principal axis for 5 is 1, 2, so across 1 up 2, and it's going to be, there's my principal axis there, and that's going to be the y-axis. So really it's just the little xy plane that's been rotated around, and of course because these are orthogonal, it'll be a Cartesian system with the two axes perpendicular. Now, so the line y equals 1 is going to simply be, we go 1 unit out here and we draw a line parallel to the x-axis through there. So that's the line y equals 1. And we'll have another one. Similarly, we go to -1 distance this way on the axis, we'll get a parallel line. So that's y equals -1. Now we could put some little bit more information in. We can see where it cuts the little x-axis, put y as 0, so we get √5 here for that one. And over here that will be -√5. And if we put x to be 0, we'll get plus or minus √5 on 2. So that number there is √5 on 2, and this will be -√5 on 2. And that's probably enough information in the picture to show what's happening. So in this case, our conic, we say, degenerated into the two straight lines here. You can actually get the equations of these two straight lines either by again going back to the principal axes, or you could just note that you can complete the square on this. This happens to be a perfect square. This is x plus 2y all squared is 5. And so that would be x plus 2y is √5, or x plus 2y is -√5. And they would be the Cartesian equations of these two lines with respect to the old axes. And so that solves the problem.